So thank you for questions, for waiting, and do not worry. Today is kind of last sip of breath before actual concentration. Please focus on the homework if you didn't start, and try to ask questions like today, because tomorrow my day is quite busy, hour by hour meetings, and it is due before the class on Wednesday. I understand that it is kind of squeezed schedule, and it is not easy. So please consider to invest about 2 hours at least for it. So do you understand what this notation is? Right? So you just multiply it by wave function. You need to scroll through nodes or through your memory for eigenstates of particle in the box. No, it should be normalized, and then multiply it twice, integrate, and see. And when it is the same, it will be sine squared, or sine 2x squared. But here it will be sine x, sine 2x times x. And some of you did it as an exercise in homework 3, extra credit. This outcome of number 2 is an input for number 3. So to do number 3 without number 2 is kind of impossible. So it will be accumulated. If you are scrolling through and think, oh, it is too heavy, let me do this one, it will not work this way for this. They come in bundle. So you can practice either Schrödinger way to predict future or density metrics, and then the matrix elements will be plugged in. So the initial state will surface, you dress it with time dependence, accumulation of phase, and then multiply it by expectation values. Also, this one is already done. Here, we were not doing neither in class nor in homeworks. And then you replace momentum with derivative, and integrals will look different. It is expected that position and momentum should oscillate here, but who knows? Maybe some of them will not. You need to check. It is a scientific question. Energy is expected to be not time dependent, but you need to prove it with calculations. This one is just free fall acceleration. This is really quick. It's like 5 minutes. This is free fall acceleration. This is free space. Okay. Anyway, that was easy. And this, I think, let's do it as an extra credit. Otherwise, it will be too much if it will be mandatory. And solution of this number 6 extra credit will serve as a really good and useful transition from chapter 3 to chapter 4. So what I'm going to mumble after I'm done with this administrative notes will be transition to new chapter. And this equation is one of the typical equations for the new chapter. So very soon, in like 2-3 weeks, there will be time for new presentations. Nothing to worry about. I want to believe that it is the easiest and most pleasant part of the course. But here is the long list. Of course, we will shorten or combine things into like divide them by 8. And I will start offering new code which is a little longer than what we did before, maybe 3 times longer, not drastically. And it will be code that with some modifications we will use for the rest of the class in the labs, and the project that will contribute the biggest portion of the grade will be based on this course. So in about 2-3 weeks, you present how well you are acquainted with this code, looking on the aspects, and it just modifies propagation of wave function in time. And then after everyone is comfortable with it, we will do individual projects by modifying it slightly. So I'm just giving heads on, so it will be not a big surprise. But it's basically a program for next couple of labs and so with lots of time spent, we finally go to another object. So it will be harmonic oscillator. You want to switch camera on the class and mumble in a freestyle. Good. So physical chemistry, wave nature of electron, predicting properties of materials and molecules, and I think we did really good in covering nanostructures. Finally, we went to something realistic from abstract models. By now, so if I need to criticize this course and sign papers to disable it or to arrest the teacher, I'm the best person because I know all weaknesses of the course. So you already noticed me telling about what is missing. By now, if we all think critically, there is one more substantial weakness. If we switch on our intuitive thinking, then molecules are not only electrons, they are positively charged ions. And if it is a realistic condition, the interatomic distances change. Even if there are no chemical reactions when bonds are broken and combined, they're not steady. Everything, when temperature is increased, everything starts moving and shaking slightly. This aspect is completely missed in every single minute, every single word I was doing before. So it looks like nothing is moving. So that ions are nailed down to the like surface, and only electrons move, and only electrons have wavy nature. This is substantial shortcoming. This is, I wouldn't say lie, but it is like lack of focus on important aspect. And I want to make an effort to compensate. So from now on, we will be switching gears and apply your knowledge of quantum theory and basics to different direction. Before we were telling that ions, we were either not talking about them or telling that they define potential, which is like different, defines the walls of the box. But what if you look on the individual ion? What if you look that it can have mass, position, momentum? What if someone kicks it? Would it move or not? And if the mass is, of course it is bigger, but if it's still a small number, is it possible to observe quantum properties of the ion? Can we think of the ion as quantum particle? That instead of exact position in space, we should set up a wave function. Is it only a fantasy in the abstract thinking, or it is something really solid that we need to take into account to predict actual properties? Are there any consequences? Are there any phenomena in the realistic world of chemistry where quantum properties of nuclei play a role? Make sense? So what do, oh, okay. I'll show some slides, but I think I can spell everything without any single picture. So what is a typical motion of ions are doing in an intact, in an intact molecule? Do they move continuously, linearly? Is they bonded to other atoms? Yes or no? Yeah. Like molecule, I keep the molecule. Like, what is the motion of my thumb if I'm standing here? Can my thumb move away if no one cuts it? No. So it's bonded. So it can move local motions in the vicinity where it is bonded. So same for ions in the molecule. If we do not let the overall molecule to translate in space, each individual atom can move only in the vicinity where it is bounded. So it can move left, right, up or down, and it can repeat it. So what's a typical word for repeated motion forwards and backwards?
A wave.
Good. And let's just play linguistics. Any other words?
Oscillation.
Super. Okay. Let's keep playing linguistics. Molecules in harmony with itself. The bond is not broken. Which oscillations are? What will be the adjective for this motion? For oscillations?
Harmonic motion.
Yes. So it's a little exaggeration, but if the oscillations are happening with a well-defined single frequency, sometimes instead of telling that frequency is specific, people tell harmonic. I don't know why. Maybe because it's related to music and harmony. So the title of today's the next 3-4 weeks chapter is harmonic oscillations. And if no one breaks the molecule on pieces, then atoms, ions are and lengths of interatomic bonds just oscillate. So we are going to apply Schrödinger equation and maybe some other tools to oscillations. And as you already know from your experience and your knowledge in the class and maybe from common sense, if one wants to play Schrödinger equation, one needs kinetic and potential energy. Kinetic energy is always the same. Potential energy depends on which system we describe. So we do need a potential for harmonic oscillations. And then we need to solve Schrödinger equation and observe consequences. So I'm not intentionally lying, but I'm not disclosing all details of the path forward. There will be some additional pleasant and hard things, but general direction is as follows. Okay, so I'm going to show some slides, but basically you already know what we are doing in the rest of the day and the month. Molecules can be formed of ions, anion and cation, then they are coulombically attractive, right? And then it is diatomic molecule. When one contracts or extends the distance between ions, so if we extend it, the energy increases because it is hard to break the bond. They attract back the equilibrium. If one is trying to contract them, bring them closer, the energy will increase as well because they have their own radius and what's the nature of the ionic bond? One transfers electron from one nuclei to another one, and it becomes like it works like positive and negative charge. But if you bring them close enough, they start to collide with their inner positive charges, no matter what are electronic clouds, and they definitely repel. And this repulsion can get really strong. So you cannot smash them close to each other if you don't have enough energy. So attractive, repulsive. And the slope of the potential energy in respect to interatomic distance is determining is a key for the physical object that we should play the wheel of fortune. So this is energy, and slope of energy is, try to guess the word.
Strength.
Very close.
Like
if someone is doing arm wrestling, you need to have what?
Force.
Yes. So the bigger the slope, the bigger the force, right? So if you have potential, you instantaneously have the force. Okay. So I'm going if I do not forget the slides that I prepared years ago, I'm going to focus on the region only near the equilibrium, because this dissociation limit and collision limit is not regular thing if in normal conditions. I'm going to look only in onto this region. So right now, if we look on the small elongations and contractions near equilibrium, how would you describe if you need to write a mathematical function for this region of the potential?
X squared.
Super. Thank you, Jared. So we are repeating the glorious path of science on the Earth. So it's natural thing to forget about this complicated unsymmetric thing and just use X squared. So because it is so much attractive by its simplicity. Yet if one does want to set up this X square thing, one can define it also if positions of ions are three-dimensional in the vector space, right? It still will be offset from the equilibrium, difference of radius vector square. So I think it is maybe the only non-trivial slide in today's meeting. I didn't have an idea how to extend it to 50. It's not possible. So mathematically, what is the Taylor expansion? Right. So you're familiar. This is not a new concept. And how can I formulate verbally what is Taylor expansion? Sure, but if I do not have slides, like Fourier transform is an attempt to represent arbitrary function as a summation of oscillating sines and cosines. Taylor expansion is an attempt to represent arbitrary function as a summation of x squared, x cubed. What's the common word? You know this word because you know ancient political systems. If you have like democracy, tyranny, oligarchy, you know monomers, oligomers, and polymers, right?
Okay.
So
It's a
polynomial function.
No.
So Taylor expansion is an attempt to represent arbitrary function as a summation of polynomial function, or as a polynomial function, as summation of different powers. In Taylor expansions, or in our basis expansion, we just use this expansion coefficient C capital sub f, right? And they were in front of basis functions which are different in each chemical system. In math, in Taylor expansion, expansion coefficients are known. So there are theorems, and it is like very natural. What are the expansion coefficients? They are not arbitrary stuff that we need to select in a known way. They are, what does prime means? Single prime, two prime.
Derivative.
Yes. So by taking a first, second, and third derivative in the vicinity of point A, one immediately represents this any function, any good function, mathematical good function, which means it doesn't have discontinuity. Any mathematical function as a summation of this power polynomial stuff. And the derivatives serve as expansion coefficients. Typically, the lower order contributions are bigger and higher order contributions are smaller. And you can see it from 3 factorial is 6, 4 factorial will be 24, 5 factorial will be, I do not have skill to do it, but something like 5 times 24, 6, bigger. 5 times 20, 180,
Or 120.
5
Closer.
times 4,
Closer.
20. 20 times 3,
Uh-huh.
60 times 2, 120.
Yes. Good. So the denominator will be 1 over 6, 124, 120. So even if the derivative is big, which is not typical, the higher order terms typically are vanished. And there is, based on the theorems provided to all of us at freshman years in calculus, any good function can be expanded in Taylor series and higher order terms drop. So I'm going to play Taylor order expansion of the interatomic potential without even writing down the function explicitly, just by hand waving. And in essence, I will just repeat the same what Jared told by one word, x squared. I just will try to justify. So if no matter what this function is, we apply Taylor expansion in the vicinity of equilibrium, then the function potential as function of elongation will be value of potential near equilibrium, then first derivative times x. Now let's think critically. If it is a minimum, minimum means the tangential. So first derivative equals
0.
right. So we can drop first derivative. Now we have second derivative, x squared, 1 over 2 factorial, just from our calculus theorems. And this will be the discovery of Jared, x squared, elongation squared. The steepness of this parabola will be second derivative of the actual potential. And if you have it, we can take derivative, second derivative, or we can just assume some constant there. And then we know from our previous experience, from our intuitive expectations, that it is a normal thing to drop higher order terms. So just stop acting here and say, because of this, the potential, interatomic potential will be just a quadratic function. No objections. So you didn't have objections, and the academic environment didn't have objections for the last 200 years. So we are on the right thing. If there are higher order terms, one can call it unharmonic corrections. But right now, we will be busy without it. The same thing. Well, a little namings and nomenclature. You see, I'm trying my best to expand the story for a long time, but it's really short. So, who designed this law and what does it mean? If you can read it.
Hooke's law.
Yeah.
For mass on a string.
Spring. Who was Hooke? Which year?
Physicist.
Physicist. Yes. So it was a jerk and competitor of Newton, who was telling that everything Newton derived is wrong. But he was making his positive contribution as well. So the force is on harmonic oscillator spring is directed opposite to the direction of elongation. So if elongation is positive, force is negative. If elongation is negative, force is positive. And the proportionality coefficient is Hooke's law. What is the connection between force and energy? So force is slope of energy, or in other words, derivative of energy. And then if force is derivative of energy, what is energy? If you have two functions, by taking derivative of number 1, you get number 2. How can you get from 2 to 1?
Integral.
Super. So energy is
Integral
force. So excellent. So if you integrate linear function, you get quadratic function. So you can get this quadratic thing even without this Taylor expansion, just if you believe Hooke's law. So the stuff here is so 1/2 just comes from integration. This is Hooke's constant, rigidity constant. The bigger the constant, the stronger is resistance of the spring. If you have some mechanical thing with a spring, and I don't know if you had this toys that you compress the spring and then it moves. So then it oscillates, elasticity constant, and if we put a ball of heavier mass to the same spring, we would move, we would oscillate quicker or slower with additional inertia.
Quicker?
Huh?
Quicker? Because it's heavier?
No,
Slower?
right? Because inertia is resistance of a mass to external forces that want to give it acceleration. So it's, I wasn't thinking about it. One could probably bring in class like springs and balls and try to make them oscillate. So the heavier mass takes slower, and frequency becomes lower. So frequency is square root of elasticity over mass. And this is angular frequency, and if one just needs how many beats per second, it's correlated with this 2 pi constant. So if one takes square of this expression, it will be frequency squared times mass will be elasticity. It's not a big discovery, just plain and Drushafin things in the order. And for the exercises that we will be doing for chemical physics, instead of using elasticity constant, it's better to speak about frequency and mass. So we will try to use mass frequency squared over 2 elongation. This is the potential of ions and atomic bonds when they're not broken, when they're near equilibrium. So from now on, here is the summary. Elongation, elasticity, mass, angular frequency. So from now on, we do want to plug this stuff into, maybe only for this slide, it's time to share screen. So we plug our square of the elongation as the potential energy. And here I use this R because I do not want to be specific about X. For example, if you have diatomic, who knows whether it is oriented along X, Y, or Z? It's just distance between atoms. So letter R comes from here. Then kinetic energy is just second derivative over this elongation constant, and potential energy is square of elongation constant. So if I do plug this total energy operator into Schrödinger equation and do it explicitly, then we are getting time-independent Schrödinger equation for harmonic oscillator. And under harmonic oscillator, we understand pair of ions or maybe bigger molecule where one ion is moving in respect to its binding point. And we will assume, or we will explore through our exercises, that quantum properties of ionic motion sometimes plays a role, or we will assess how what are the quantitative criteria to take it into account or to neglect. It is a big hope that in many things one can neglect it, otherwise the life will be too complicated. But we need to, like, if you have a competitor, you need to know properties and strengths and weaknesses. When you need to take it into account, when you can neglect. So, what about this equation mathematically? Is it possible to solve? Are there any challenges? So we have second derivative of unknown function. We have unknown function, which is typical. We already had it. And here we have unknown function multiplied by polynomial. I wouldn't say that it is a really bad situation, but it is an additional challenge. So we need to find, same as for majority of all solutions of Schrodinger equation, there will be more than one solution. So same as in particles in the box, there will be a set of eigenstates. You can put, there will be numbers and for energy and for states, and they will be offset at certain energy. And the solution of this equation is does not have expression in terms of standard functions. Like you cannot represent it only as exponential, only as sines and cosines, only as polynomials. It will be series. It will be like polynomial times Gaussian exponential. And in such situations, when elementary functions do not give us solution, differential equation, people tell it is a special function. So solutions of this equation is represented as special functions and Hermitian polynomials. But as we go through the class, I will try my best to avoid it and offer a shortcut. So next, about a week from now, except Wednesday. Wednesday we will analyze and I will show the key to the homework that I hope to get submitted. But then we will focus on solving this equation, and then we'll go back into the time-dependent part. Another note, it's not like a regular class material, but maybe to make connections to the stuff that you were doing before. Remember in the homework that you have submitted about density of states, there was one special case when density of states is flat. It doesn't depend on excitation. What was it? How many dimensions?
0.
No. 0 is like was few fixed. When it was flat, like density of state was constant as function of energy.
2D, right?
Yeah, 2D. So in 2D surface, density of states doesn't change, which means number of states per energy interval is the same. So, which means offset between nearest eigenstates is approximately the same. Just a little heads up. Very similar structure of eigenstates, very similar density of states will be observed while we solve this equation. So they will be offset by the same energy intervals. And this property makes harmonic oscillator of any nature a favorite toy for all theory considerations. So if you want to be a scientist, you want to publish papers and you do not know what to do, just can practice about oscillator. Where will you meet this in your academic career? Next semester, you'll have thermodynamic and statistical thermodynamics, and there it will be much more degrees of freedom, much more like there will be ensembles. So instead of one interatomic bond, one electron in one box, you'll have like infinity, large number. And when you have a large number of very similar systems, if they have specific and different electronic properties, it's a killer. It's not possible. The only model when one can go over ensemble of the big, large number of the same replicas of similar systems is harmonic oscillator. So it's the oscillator, and specifically its spectrum of energies will be used very extensively in the next course. Do I have anything else? I hope not. Oh, okay, here is this solution for the ground state. And if you look at our favorite Gaussian function, so in the ground state, it will be exponential minus some constant elongation squared. So the probability to find nucleus near the equilibrium is the maximum. And as far as we elongate to the left and to the right, it will be less and less. The width is this Planck constant over mass and frequency. And if the mass is big, then this width becomes very small and you can neglect quantum properties. I hope this is a lesson.